Welcome to our second video on our Year 10 Chem 1 unit, and this is revision on bonding. So we've got our three types of bonding, remember? So we've got our metallic bonds, which is where a metal bonds with a metal. We've got our our covalent bond, where a non-metal bonds with a non-metal, and we have our ionic bonds, which are metal and non-metal. And when you look at these guys here, we've got our ionic bond, where our non-metal is giving the non-metal the electrons. We've got our covalent bond where they're sharing electrons, and our metallic bond where neither of them have got the electron is free between them. Okay, in the last video we talked about our anions and cations. Okay, and here we can see our neutral sodium atom here, and here we've got a sodium cation with its electron that's been removed. Okay, so remember, in a cation has more protons than electrons, giving them the charge, or depends on the difference what the charge is. In this case it's a difference of 1, so our sodium cation has the charge of +1. And we look at that in the picture here. We've got our balanced sodium atom here with that 1 electron, and here that single electron is being removed. We've got more protons and electrons giving us that overall charge of +1. Here we're looking, sorry about the quality of this picture, but we've got oxygen. Okay, and we have oxygen, and that has 2 electrons. That needs to gain 2 electrons to have that full outer shell, because that outer shell there's got 6 electrons in it. So it needs to gain 2 electrons, and our ion of oxygen then is what we call an anion, and it's got 10 electrons, but oxygen's only got 8 protons, so then it's got a charge of -2. There we're looking at oxygen now. So we've got 8 electrons balanced with 8 protons, so that's that balanced oxygen. And here we've now got 8, 9, 10 electrons and only 8 protons. So there's more electrons than protons. That gives it that negative charge because electrons are negative. Alright, so one thing you need to think about is the electrostatic attraction and repulsion. Opposites attract. Repulsion occurs between the same repel. Okay? Alright, so quickly just remembering metal. So a metal is an element that loses outer shell electrons. Okay, so they form cations. Metals form cations. And this is just saying that if they lose those electrons, then they become an ion, and we've said they become a cation. Now, metals have a range of properties that are listed there, and the reason they have the properties is all down to what's happening on their atomic level. So metals conduct electricity in the solid state, and this is because they have those free electrons between the particles that pass the electricity through the solid. Okay, they're malleable and ductile. And this is because the forces between the particles must be able to adjust when the particles are moved. Okay. Metals are lustrous or reflective, saying that they can reflect light. Okay, so it's just giving you the property and what it tells you about its structure. Okay, now metallic bonding. Okay, so metallic atoms have what we call this low electronegativity. Okay, so low electron attracting power. They don't want to gain any electrons, our metals, they want to give them away. Okay, so generally their outer shell will release the electron rather than gain. Okay, so metals always form cations because they release an electron. They then have more protons than electrons. So those free electrons that are released in our metallic bonding are in a pool of electrons around the cation. So you can see that here. Each of these are cations, so metal cations, and these are the free electrons that they've got rid of out of their outer shell. Now, positives and negatives attract, so all these guys are held together by these electrostatic forces between them. Alright, moving on to our next form of bonding, ionic bonding. So, metallic bonding, the ions are in a sea of electrons, and that positive and negative attraction holds them all in place. Ionic bonding is a little bit different. Ionic bonding is that transfer of an electron. So you have your metal atom and you have your non-metal atom. So remember, ionic is metal to non-metal. And what happens is our metal literally gives the non-metal an electron. Then you've got a positive and a negative that have that electromagnetic force between, that electrostatic force between them to hold them together. You've got a positive and a negative ion. So here we've got magnesium and 2 chloride ions. Okay, so this is showing that you can, one ion, so one anion here can share, one cation here can share electrons with 2 anions. Not a problem, they all want to be balanced to some extent, okay? We've got 2 cations here with aluminium bonding to oxygen. Okay, so how do we write these ionic formulae? We've got some rules. Okay, so we always put the cation first. So if you've got aluminium oxide, you can't call it oxygen or oxide aluminium. You always put the cation first and then the anion. Remembering that the net charge must be 0. So if you've got a charge of 2 plus and the charge is negative 1, then that's not equal. Somehow we need to balance them up. Okay, and we'll look at that in a second. We do have just a couple of things that you need to remember. If we've got some ionic compounds, like iron, they can exist as a 2 plus or a 3 plus cation. So you may see something like iron 3, that means it's a 3 plus. Okay, so you'll see that for some elements. Alright, so when we name the cation, we just need to check that bit, but we put the cation symbol, so for example Fe, and then how many electrons how many extra protons it has compared to electrons, so what its charge is. Then we've got to name our anion, and we do something similar here, except we change the ending. So if it's oxygen, it becomes oxide, if it's sulfur, it becomes sulfide, and so on. Iod tells us that there's only one element, so there's only oxygen or there's only sulfur in that part. So sodium nitride, there's only sodium and nitrogen. Okay, nitride. So nitrogen is the element, nitride is telling us there's just one. Alright, so the swappy bit. So we've written our compound down with the charges. Now we need to balance it, because at the moment we can't have a 3 plus and a 2 plus. So what we need to do is we need to say, okay, if we have 3 oxygen and 2 aluminium, that charge will be balanced. That's why we do the swap. We've been doing lots of that in class. Okay, so the structure of our ionic substances. So they're made up of these negative ions. They will be in a 3-dimensional shape, which quite often think 2 dimensions that we look out on the screen, but they're actually 3-dimensional. They form a bit of a lattice that forms by an electrostatic force between the oppositely charged ions. The ions in the lattice will be packed really tightly together, so the ions with the same charge are kept as far apart as possible, so trying to keep that opposite, that repulsion between 2 of the same. Alright, so we move on next to covalent bonds, and this is where we've got 2 non-metals, or 2 or more non-metals, and they share electrons. So covalent bonds are not between non-metals. Now we have different types. We have our intra and our intermolecular bonds, which we'll look at in a minute, in a moment. So we've got intra. Now this occurs within the molecule. Okay, so within the molecule. Here, between two molecules, there may be a weak force, and that's an intermolecular. So intra is within the molecule, inter is between molecules. So intramolecular bonding is our covalent bond, okay, and that is where two or more atoms are sharing electrons. You do just sometimes get this extramolecular force. So non-metals have this high electromagneticity, so they want to gain electrons. They attract them very easily, but they don't give them up. Okay? So two non-metallic atoms, they want to keep their electrons and make their shell full. So they share electrons with others, so they don't have to give any of their own up. Some covalent elements, we've got hydrogen there. Hydrogen wants a full shell, so that's two electrons in that first shell for a full shell. So there we are with our hydrogen molecule H2. They're sharing their electrons. Now when we draw our covalent molecules, we use what we call Lewis diagrams. Okay, so you've got your electron dot diagram there, but what we want is the Lewis diagram, which shows just the outer shell. So if you put all the shells, then it gets far too complicated, whereas if you give just the outer shell, then you can show those two electrons being shared here in our chlorine molecule. Okay. Remembering that the two electrons here are called our bonding electrons, and then these are non-bonding and lone pairs. They're not involved in the actual bonding part. Okay, rules for drawing our electron dot diagrams. Draw the dot diagrams for each of the atoms in the molecule. There you go. When you do draw them, you need to be cleverer than this. You'd move that one over that side, or actually that one over that side, so that they can share. I couldn't get that image, so I've just had to put this one up for a minute. You need to identify the unpaired electrons. So for example, if you had that one there, then you could say these two are the unpaired. So all the other electrons are not going to be involved in the bond. The atom with the most bonding would go in the centre. So if you had if you had several atoms bonding and one had 4 other atoms bonding to it, that would go in the middle. So you see some results. Okay, second. Okay, then basically you identify the atoms that are sharing like that, and check that each electron has a pair. So they're all paired up, nothing's free, we're happy. Okay, so Lewis diagram for nitrogen. So here we've got nitrogen with 1, 2, 3, 4, 5 electrons in its outer shell. So this one, 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. Now we want 8 to be balanced. We've got 1, 2, 4, 5, 6, 7, 8. So by sharing, they get 8 in their outer shell. And remember, it's hydrogen is 1. Okay, now structures. You can draw these structural diagrams, so they have the lines. Okay, and then remembering that behind that is the fact that there's some 3D structures, which we're not going into on this video. One line represents one pair of electrons. So that's a pair of electrons represented with one line. And finally, how do we name our covalent compounds? When naming anions with only one atom in it, we give it the name that it is, but we will change that ending. So the end of an element is removed and we put "ide" on. So for example, oxygen becomes oxide, it's only got oxygen like I said earlier. So yes, we use "ide" for anything with just the one element in it. We'll look more into that at the end of the next video. Thank you for watching.